So today we continue our study of the determinant, studying further properties of this determinant. So determinant part 2. Let's start with very important properties. In this property, so you remember when we studied Gaussian elimination, that we can apply on matrices so-called elementary row operation, where we work only on rows, and we have three. We can swap the rows, we can change one row to a multiple of this row, or we can add to one row a multiple of another one. Okay, this was the three operation. Now we would like to study how behaves the determinant with respect to this operation. You will see the use of this property right after that. Okay, so the theorem, let's call it theorem 4, and this will be elementary row operations and determinant. Okay, so we start with A, B, A, N times N matrix. And then we call B. B is obtained from A by the elementary row operation. Row I is lambda times row I. Okay? So this is one of the row elementary operation. Then what happened for the determinant? Well, the determinant of the matrix B will be equal to lambda times the determinant of the matrix A. Now let's study what happens if we swap the rows. If B is obtained from A by a swapping of the rows, so row I, row J, let's say, then the determinant of B will be minus times the determinant of A. So, as you can see, swapping two rows will introduce a -1 modification. And thirdly, okay, so if B is obtained from A by an operation, so you remember the third operation, I take one row and I modify this row by adding a multiple of another row. Then what happens? Seems like a complicated operation, but the result is that the determinant of B remains unchanged. So the determinant of B will be exactly the determinant of A. So as you can see, if we do these three elementary row operations, we have only two that are going to modify the determinant. The first one is multiplication by a scalar lambda. This will, so the determinant will also be multiplied by this lambda. In swapping, you will introduce a -1. Okay, so I'm going to give a sketch of proof of this property. All right. Let's start by proving property 2. Okay? So if PA is a pattern for A, and that I do operation 2, which is swapping, then PB formed by the same entries is again a pattern. So you have to check this. You can take the example of a 3 by 3. You have 6 patterns, and please just try, and you will see that if you swap 2 rows, you will get, by taking exactly the same entries, so the position of these entries will be different, but it will be still a pattern. It's still a pattern, and the important fact is that, of course, because you take the same entries, then the product will be exactly the same. And the sign will be modified. So the sign, you will have a different number of inversion, and if the sign of PB will be equal to -1 the sign of PA. So please check that. You can check in the example 3 by 3. Now let's prove 1. Okay, so here what are we doing? So we transform a row by a scalar of this row. So taking PA, then PB, what will it be? It will be same pattern, except that the entry in row I will, so let's say BI will become lambda times BI. Okay, so obviously the product of PB, as you can see, will be equal to lambda times the product of PA, and also the sign. The sign, well, this is about the number of inversion, but inversion, nature of inversion is just related to the location of the entries, not of their value actually. So because the location of the entries of PB and PA are exactly the same, the sign of PB will be exactly the sign of PA. And so, as you can see, we will have finally determinant of B will be equal to lambda times determinant of A. Okay, so this is not difficult to understand. Now, to prove 3. So 3 is the most surprising because the operation is quite complicated. You replace a row by a multiple of another row. So the surprising fact is that the determinant is not modified. So in order to prove 3, I'm going to give you just an intuition that this is working. First, you are going to observe that and I call this property actually property 4. If A has two identical rows, then the determinant of A must be 0. Okay, so let's prove this proposition 4. Well, by the property 2, you remember that if you swap two rows, then we will get a minus times the determinant of the other. So, for example, if we swap the two identical rows, then the determinant of B will be equal to the determinant of A. This is because we have swapped two identical rows, and so B is equal to A. But also by property 2, this must be also minus determinant of A, just because we modified by a swapping. And so you see that we get determinant of A equal minus determinant of A, which means that determinant of A equals 0. So this proves this property 4. This property 4 will help us to prove property 3. Now, another fact that I will need is the following. So secondly, you can observe that we have the following properties that I call number 5, and which is the following. So the determinant function is what I call linear with respect to rows. And I explain next what I mean by being linear with respect to rows. So this means the following. If my matrix is of the following form, so I have, for example, row 1, row 2, and here I'm interested to prove modification by operation 3, isn't it? So let's have a look. I'm going to take here for the ith row, okay? I will take row prime I plus row prime j. So I will just add two rows, and then the other rows are as usual, row I plus 1, row n, okay? Then the determinant of A will be actually the determinant of first the matrix obtained by row, so row 1, row I minus 1, and then I take row prime I here, and then I take all the other line, row n, and finally plus the determinant of row 1, row I minus 1, and then I take the other one, row prime j, and I finish the same by row n. So that's what I mean by being linear with respect to rows. It means that if I can write one row as a sum of two rows, then the determinant will be the sum of the determinant of the first row and the second row. So actually we will admit this property 5, which is a little delicate to prove. assuming that we have this, we can prove our property 3. Okay, so let's see. So I'm starting from a matrix with row 1, row n, and then my transformation is that I will get a matrix 1, matrix I minus 1, and when I arrive to matrix I, to the row I will do row I plus lambda times row j, right? And then next I will have I plus 1, and finally row n. Okay? So if I apply, we apply 5, what do we get? We get that the determinant of this matrix, so let's call this B, this will be equal to the determinant of the first one where I just take Ri, okay? And so this will be actually the determinant of the matrix A. And I will take a determinant of a matrix where I modify only one row, and I have multiplied this row by, so this is at the position I, by the way, I's position. And here I have taken lambda times the row j. And j was somewhere else, right? Okay. So, as you can see, I just need to prove that this determinant is 0. If it is 0, I will have my formula that B equal that of A. Now, why is this 0? Well, here I can apply so which property was that? It was property, yes, it was property 1. We apply 1. We know how to behave a matrix where we multiply a row by some constant lambda. So we know that this is actually, so let's write that B plus, so this is equal to that A, and this one will be actually plus lambda times the matrix, the determinant of a matrix which will have as row. So here in I's position I will have row j, but again in j's position I will have again row j, and the other row I don't care. But the important is that this matrix, as you can see, has two rows that are identical. And now we can apply 4. So applying 4, I get that this is just that B will be equal to that A plus 0. So this is necessarily 0 because I have two rows that are identical. Okay, so this is a sketch of proof that when you do this difficult operation where you replace a row by a multiple of another row, the determinant strangely is not modified. So this is the explanation actually of these nice properties. Okay, now let's have a corollary of our theorem. So now we know how to behave a determinant when we apply one of the elementary row operation. Corollary. Let A be a n times n matrix and B obtained from A by a sequence of elementary row operations, okay, finite sequence, where we used, okay, so we used S swappings and constants K1, Kr. Then the determinant of B will be equal to -1 to the power S, the number of swapping, times the constant K1, Kr, the product of them, and times the determinant of A. Remember, by the previous theorem, you don't need to remember in this sequence of elementary row operation. You don't need to remember the third kind of operation. You just need to remember operation of type 1, swappings. So how many swappings and how many scalar or constant K1, Kr you have used when you have transformed a row into Ki times this row. If you remember these two data, then you can predict the determinant of the transform matrix. It will be -1 times the number of swapping and times the product of the constant you use times the determinant of A. Okay, so this will be very useful. We can see immediately a second corollary. Corollary 1, okay, and corollary 2 is that let A be a square matrix, then A is invertible if and only if, okay, I use this symbol for if and only if, the determinant of this matrix is actually non-zero. So this gives a brand new criterion to know if a matrix is invertible or not. Remember that by definition, a matrix is invertible if and only if there exists some matrix B such that A times B equals B times A equals the identity. Okay, so this was our definition, and now we have a new concept. We can check immediately that the matrix is invertible if and only if its determinant is non-zero. Okay, so let's see the proof of this fact. By the way, the proof of corollary 1 was immediately coming from the previous result. Okay, this is very easy. To prove corollary 2, you observe the following. So, if A is invertible, then what you know for sure is that this you know by the Gaussian Gauss-Jordan method. You remember you do on the left, you do an augmented matrix with on the left side A and on the right side I. And at the end, if the matrix is invertible, you will find on the left side I and on the right side A minus 1. So you know for sure that the RAF of this will be the identity matrix. Okay? Now the determinant of the identity matrix, what is it? It is well, it is an upper, lower, and lower triangular matrix. So its determinant is a product of the diagonal entries. The diagonal entries are just 1, so the product of them is still 1. In particular, it's non-zero. Okay? But by corollary 1, we know that that of the RREF of A will be -1 number of swapping times some constant and times the determinant of the original matrix. So this will be non-zero. Therefore, we can deduce that all terms here are non-zero. In particular, that of A is non-zero. Okay? Now, second case, if A is not invertible, okay, then the last row of RREF of A, so it cannot be the identity matrix, and necessarily it means that one of the last row contains only zeros. Okay? So if it is invertible, its RREF is the identity, otherwise it will be a matrix with, as a last row, a row full of zeros. So it means that the determinant of the RREF form of A will be equal to 2 times the determinant of the RREF form of A. So this is by actually linearity of the determinant with respect to rows, because a row full of zeros, you can write it as 0, the row 0 plus the row zeros, and therefore it will be the sum of the two, which will be the same matrix. So you will get 2. But if that RREF of A is 2 times that RREF of A, it means in fact that this determinant is actually equal to 0. And again, by corollary 1 this time, you know that this is equal to -1 times the number of swapping, so non-zero, times some non-zero scalar k1, kr, times determinant of A. And this is 0. This is not 0, this is not 0, so it implies that that of A is 0. And this proves corollary 2. Okay. So, application of this result, these properties, is the following. Application to calculation of determinant so we can use the Gaussian elimination technique. Keeping in mind the number of swapping and also we need to remember the scalars Ki used for operations of type Ri change modified to Ki times Ri. Okay, we need to remember when we apply the Gaussian elimination, these two numbers, the number of swapping, so it was called S, and this scalar Ki. Then we have determinant of A will be equal to -1 times S. Then these scalars K1, Kr to the -1 times the determinant of the RREF. This is just a modification of the formula of corollary 1. So on corollary 1, this was on the left side. So I just divide by this, and you can see that -1 times S is still good. So this formula is totally correct. You can predict the determinant of A knowing the determinant of the RREF matrix. Remember, the RREF form of A is much more simple, and for example, it will be most likely upper triangular or lower triangular, okay? So you will be able to calculate the determinant of this very easily. Let me give you an example, or I will put it as an exercise. Let's put it as an exercise. Exercise. Use Gaussian elimination to calculate determinant of the following matrix: 0, 7, 5, 3, 1, 1, 2, 1, 1, 1, 2, -1, 1, 1, 1, 2. Okay, so try to do that. You will start from this matrix. This will be your augmented matrix. And you use elementary row operation. So you follow the technique. First, you find a pivot. So for example, we can swap these two rows. You get your 1, then you erase the other entries. Then you go to you push the cursor on the right and below, etc. You do that, and you remember always the swappings you have done, and you remember also the constants that you have used, and then you can use this formula to deduce the determinant. You will see it will get very easy, even though it's a 4x4 matrix, which is quite long. Okay, let's see another property of the determinant, very important one. Let's call this theorem 5. The determinant of a product of square matrices, so A and B, B2, n times n matrices. Okay. Now the determinant of the product is actually the product of the determinants. So this is also very important properties of the determinant. Okay, let's give proof of this fact. First of all, if the matrix A is invertible, okay, then in this case we can compute the RREF form of the following augmented matrix we put A on the left-hand side, and on the right-hand side we put AB. Then we know that the REF form of A will be the identity. So here we will get the identity, and here we will get A minus 1 times this product on the left. So we will get A minus 1 AB. So as you can see, A minus 1A is identity, identity times B is B. So everything, so this is identity, and therefore this is nothing else as B. So we will get identity and B. Now, using corollary 1, which gives us, yeah, we can use also the last corollary. So we get determinant of A just by looking before the vertical bar and after. So this equation gives us the following fact. It tells us that the determinant of A is equal to, okay, let's say minus 1 times the number of swapping. Then we have used this constant, and then we get the identity, right? Because it was it was invertible. So this is our REF form. The determinant of the identity is 1, right? Okay. But we get also the following fact just by looking at the right-hand side. So the det of AB, this will be what? This will be again minus 1 times S, the same scalars, K1, Kr, and then determinant of B. So we get this by just looking at what happens on this side, right? So this, the REF form of AB is just B. So using this, we get this formula. And, okay, now we can replace this equation here. So this is by the first equation, this is, first part is just determinant of A, as you can see, and then we get determinant of B. So if the matrix A is invertible, we get our formula. Now, if A is not invertible, then we know that the determinant of A in this case is 0, isn't it? Which means that on the right-hand side, we will get 0. We must prove that determinant of AB is 0. Okay, so we need to prove that is, we need to prove that AB is not invertible. Okay. Now, how do we prove that matrix AB is not invertible? We will do that by a proof by contradiction. Proof by contradiction. This is something very important in mathematics. So, to prove by contradiction, you are going to assume the opposite of what you want to prove. We need to prove that AB is not invertible. So, we are going to assume that AB is invertible. What does it mean that it is invertible? It means that, okay, So this will imply that there exists another matrix C. There exists, so this symbol means there exists. And this matrix C will be such that C times AB will be equal to ABC will be equal to the identity matrix. Right? But then look at that here. By associativity of matrix product, we can conclude that A times BC equals the identity. And this will imply that A is invertible. But look at that. We were in the case where A is not invertible. So this is a contradiction with our hypothesis. It's a contradiction, which means that this hypothesis is wrong, and this is how we do proof by contradiction, so AB is not invertible. Okay. Good. Let's see an immediate corollary of this important theorem. So remember the theorem, the determinant of a product of matrix is the product of the determinant. And important corollary is the following. If A is an invertible matrix, then the determinant of A minus 1 is equal to 1 over the determinant of A. And the proof is, of course, an immediate consequence of the previous theorem. I would like to finish this section on determinant by the following Laplace expansion theorem, which is a very convenient tool to calculate determinant of matrices. Okay, so first of all, I need the following definition. Let A be a n times n matrix, and let Aij be the n minus 1 times n minus 1 matrix obtained from A by omitting row I and column, so the column Cj. So you remove the row I and the column j, and you will get n times n minus 1 matrix called Aij. This is called the Ij minor of A. we have the following theorem, which allow you to calculate very nicely determinant of n times n matrix using the determinant of lesser rank matrices of rank n minus 1. So, namely, we have two parts in this theorem. First of all, you can expansion down the j's column. Okay. So the following is true. The determinant of A will be the sum for I equal 1 to n of minus 1 to the power I plus j times aij times the determinant of the minor aij. So formula is very easy to remember. You modify, so here it's down the j's columns, which means that j is fixed. J is fixed, so you do the summation with respect to I, because j is fixed. And here minus 1 I plus j aij times determinant of the minors. And you have the other equivalent formula, which will be the expansion with respect to the i's column. I's row. Okay, so here, this is basically the same formula, except that this time I is fixed, which means that the only modification to the formula will be that instead of taking the summation over the I, you take the summation over the j. 1 to n, it's a square matrix, so n times n. And then the formula, the remaining formula is exactly the same. Minus 1 times I plus j times aij times the determinant of the minor capital Aij. Okay, so you see these two formulas are extremely identical. The only difference is that first, either you expand with respect to a column or with respect to a row. Just an example of this is actually something that we have used when we gave the definition of the determinant of a 3 by 3. So remember when we had A11, A12, A13, ANN, we take A33, okay? So the determinant of this, remember, I told you that it was, so I can expansion formula with respect to, so I'm going to expand with respect to the first row, okay? First row, so I use this formula. Now j goes to 1, 2, 3, n equals 3. And the first sign is, so you start with a sign, okay? I is fixed, so I equal 1 is fixed, okay? Now just j will vary, and then it varies from 1 to n. So the first here is j equal 1. 1 plus 1, so you get a plus. And plus what? You will get A11. So A11. And then you get the determinant of the minor. And the minor is obtained just by removing row 1 and column 1, which means that you will get the determinant of this A22, A23, A32, A33, which is pretty precisely what I've written. The next term is j equal 2. So I equal 1, 1 plus 2 is 3. So I will get a minus a1, 2. And then determinant of etc. Plus a1, 3. Determinant of, yeah. You can check, you will find exactly this formula. Okay, I will stop here for determinants. Thank you very much.